Good evening, everybody. God, I love that song. Right, we are ready to get going tonight. Tonight's lesson, we are on forces and moments. Okay, so we're going to try and make up for our last lesson where we said we were going to try forces and we didn't. We spent the whole time doing motion. We're going to try and squeeze two topics into one here. So you're going to be quick and really nasty through the ideas. We'll do that really fast in terms of like what we need to know about forces, what do we need to know about moments, and we're actually going to then just do past paper questions on this one, because an awful lot of this is exposure to the style of questions that you're going to get asked in your paper. Okay, so without further ado, let's get cracking. Okay, so forces first, we'll do it for the first little while. I'm getting a bit of pinging back on my audio, so let's just adjust that. That should be slightly better now. Rip your earbuds or your eardrums if you're on headphones. Right, so forces to start with. Let's go. Okay, so this is it. This is the knowledge bucket for forces. Right? So if you know this, you know basically everything that you need to know in order to get 80% of the forces question right. Okay, there'll be a little bit of explain this or do this or something weird, but if you know this, you're pretty solidly on for a grade A standard on forces. So let's go. All right, so forces, what are they? Okay, so a force is anything that attempts to push, pull, or twist an object. If something's trying to push it, pull it, or twist it, it's a force. It mightn't be succeeding, but if it's trying, it's a force. Now, forces are trying to change the speed, shape, or direction that some form of object is going. Okay, key thing here is the word change. Change speed, change shape, change direction. They may or may not be being successful in that, but they definitely are trying. Okay, so then we have three laws by Isaac Newton that explain how forces work. Okay, the first law is this: an object will remain at rest. Okay, that is, it will sit still, or continue, that should be an or there, typo number 1 of the night, that's terrible, or continue to travel in a straight line unless acted on by a resultant force. And this word resultant appears all the time in forces, and basically it's just a fancy way of saying overall. Okay, so Newton's caveat was something's going to sit still, or it's going to keep travelling, doing what it was doing in a straight line, unless some form of unbalanced force is acting on it. So you could have something that's got 1,000,000 newtons forward in terms of force, but if it's got 1,000,000 newtons backwards, nothing's going to change. It's not going to change speed, it's not going to change shape, and it's not going to change direction. So if it's sitting still, it will continue to sit still. If it was going at 100 miles an hour, it's going to continue to go at 100 miles per hour. And this is a real trick that we use when we're setting questions for students, because if I can make something look like it's moving really fast, the automatic impulse in your head is that there must be a really big forward force making that go forward. No, there might have been a really big forward force to get it going fast in the first place, but once you're at speed, you actually only need to have no overall force on you to maintain that speed. If there was an unbalanced force forward, you'd be getting faster. If there's an unbalanced force backwards, you'd be getting slower. In order to maintain the same speed, you need to be perfectly balanced in terms of forces. Newton's first law, we'll use that. Newton's second law is generally written as an equation, F equals ma. Now, I don't like the letter F in here. I like the little F with a subscript R at the bottom. Okay, and I would encourage you to write this when you're doing Newton's second law equations. What that says is that the resultant force, the overall force acting on an object, is equal to the mass of that object multiplied by the acceleration of that object. So if you take those two things and multiply them together, that's the size of the resultant force. Or if you knew your resultant force and you knew the mass, you could find the acceleration through some maths. Okay, this is Newton's second law. Now, it's not actually written like that most of the time, but it's, you're unlikely to be asked for a full written version of this. If you're asked for Newton's second law and you write F equals ma, and you write F is resultant force, m is mass, a is acceleration, in a GCSE exam you're getting all the marks. A-level exam, different story. We'll deal with that. We'll do that next year. Right, moving on. Objects accelerate when there is a resultant force. That's a direct consequence of this. If you have a resultant force, then you will be accelerating, because if you exist, you have mass. Okay, there's not very many things that exist that don't have mass. Light and weird things, leave them alone. Okay, most large-scale objects have mass. Therefore, if you have a resultant force on them, they're accelerating. The converse is true as well. If something is accelerating, there's an unbalanced force acting on it. There's a resultant force. Okay, so still moving our way around. Forces are vectors, so direction matters. A very, 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 very big difference to me throwing my fist out that way with 1,000,000 newtons of force, because obviously I'm a super good fighter, and me throwing my fist in the opposite direction right at my own face with the exact same force. Numbers wise, it's 1,000,000 newtons. Consequence wise, it's very, very different. So when I'm deciding which way I'm going, if I say forwards is positive, then anything going backwards has to be considered to be negative. And when we get later on in our physics, when we get up into A-level physics, we start actually thinking, well, what if it's at an angle? What do we do then? But at the minute, we tend to deal with ones that are going forwards, backwards, or up, down, or they're just against each other. All right, and then finally, Newton's third law, this one here. Okay, if object A exerts a force on object B, then object B exerts an equal force on object A in the opposite direction. That is really, really, really fancy way of saying, if I hit the wall, it hurts. Why? I hit the wall. Right? I smashed my fist as hard as I could into a wall. Why did it hurt me? And it's because when I hit the wall hit me back. And the wall's not bothered by the effect that I had on the wall was not very big, but the effect that the wall had on me, because my hand is skin and bone and not as tough as brick, has a bigger effect. And the same is true when you do a push-up. You technically don't do a push-up. You actually attempt to push the ground down, Chuck Norris style. You do earth downs. When you do a push-up, you press away from you, trying to push the ground away. But because the ground is really heavy, your force doesn't really cause that much of an acceleration on the earth. So it goes nowhere, but you go upwards. But the force is the same. You push the ground down, it pushes you back up. And then finally, down here, we have W equals mg, that the weight of an object is the force that gravity pulls it down with. So W, the weight of the object, is equal to the mass of the object times the acceleration due to gravity, g, which on planet Earth is approximately 10 newtons per kilogram, or 10 meters per second squared, depending on which way you want to read that. And it's actually 9.81, but we use 10 at GCSE level because it makes our calculations nicer while still checking the skill that you have. Okay, so quick recap on our Newton's second law before we crack into some questions. We have F equals ma, and again, like I said, I don't like F equals ma. I like a little r in there for resultant force. So F subscript r is the resultant force that's acting on the object, and it is in newtons. No choice in that. If you've got forces, it's in newtons. No doubt about it. M is the mass of the object in kilograms, and you have no choice in that either. It has to be in kilograms. That's a trick. We'll be using that trick later. And acceleration in meters per second squared, and again, no choice. All the units for this equation are locked. You have to have them right. So what does this mean? Well, it means that if I have a situation like this, I've got a forward force here, or a force to the right. I don't necessarily know if it's forward, because this is a block. It doesn't seem to have a front or a back. So we have a force of 3,000 this way and a force of 200 this way, and we've been told the mass of this object is 500 kilograms. What I would like to know is, what's the acceleration of this object? Now, what we know is that this object will accelerate this way. Okay, so its speed is going to change in the right direction. Okay, so it's going to be accelerating to the right. So A equals something to the right. Now, I don't actually necessarily know that it's speeding up because I haven't been told anything about its speed. It could be going really fast to the left and this is just slowing down. Or it could be sitting still, in which case it's going to speed up going to the right. Or it could already be going to the right and then speeding up. Any of these are possible. Acceleration just means your change in speed in that particular direction. Okay, so we're going to calculate that. And how we do that is we do F subscript r is equal to the mass times the acceleration. And here's our problem. If I just say F stands for force, and we're like, well, we've got two forces. We've got a force here and a force here. But because I very sensibly said F subscript r, I know it's like, this is the overall force. So what is the overall force here? Well, we've got 3,000 newtons going to the right, and we want to take away the 200 going to the left, and that's going to leave me with 2,800 newtons in total, and that's going to be to the right. And it's a good idea just to put a wee arrow beside it just to understand that's the direction that we're going. So we substitute that into our equation, and we get 2,800 is equal to 500 multiplied by A. Okay, we don't want 500A, we just want A, so we divide both sides by 500. So we're going to divide this side of the equation by 500, and we're going to divide this side of the equation over here by 500. So a little slash for 500 because dividing signs are hard to come by. Grabbing our calculator, and we do 2800 divided by 500, and I get, would you believe it, 5.6 is equal to A. That's mathematically correct, but we need to turn that into an actual answer. So that we turn that around to give A equals 5.6. And I know that I put my forces in newtons, like the good boy that I am, my mass went in kilograms, which is right again. So that means that my acceleration has come out in meters per second squared, and I have my answer. All right, so that is the basis of this and the basis of the math around it. Let's take a look at some of the questions that have been posed recently. Well, this is the 2018 series of exams for CCEA. Okay, so what we've got is we've got a car, so that's handy. Forces acting on a car is shown below. We have frictional forces of 800 newtons, so that's backwards 800 newtons, and we have an engine force of 2000. The car accelerates uniformly at 1.2 meters per second squared. Calculate the mass of the car. You're advised to show your working out. Okay, so we've got 4 marks here for this. So let's take a look. What we know, frictional force, engine force, uniformly at that, mass of the car. So what do I know? I know that the resultant force, Fr, is equal to 2000, take away 800, which is 1200 newtons, that way. Being good and doing it exactly the way we were shown to do it earlier. What else do I know? I know that the acceleration of the car, A, is 1.2 meters per second squared. And we're going to assume that's also to the right because cars tend to accelerate forwards. We use different terminology if it's slowing down. And we want to find the mass. M is unknown. Now, having this little shopping list at the side of your question is a really good idea. We haven't got an equation yet, but by listing these things down, you can go, all right, I've got F, I've got A, I've got M, what's my equation? And it's handy because we're on a stream at the minute, that that's the only equation we've looked at, but when you're in an exam, you have 15, 20, 30 equations in your head. It's a good idea to make a little list of what the question gave you. That way, it jogs your memory. So the equation we want is Fr is equal to Ma. And we'll get our first mark for that. Then we get 1200 is equal to M times 1.2, and I'll write that in bracket form if that's all right. Any objections, we can check that in the comments. Now, we get 1 mark here for the equation. We'll get 1 mark for the substitution on this side, and we'll get 1 mark for the substitution on that side. And that seems quite generous, okay? But in fact, it's not really, because this side, I needed to do a calculation to get that. So there was a bit of thinking required here, and this is the general substitution mark that we get for doing good work with formula. And then finally, in order to get the mass, we need to divide both sides by 1.2, grab our calculator, and we get 1000 kilograms. Right? Here I have completed my entire working out up in the working out section, and now I transfer my answer of 1000 onto the answer line. This is a really important point. Always finish your working out up here and then transfer your answer into here. Because if this answer happens to be wrong and you hadn't transferred it, you would get no mark here. But maybe there was like a mark here, a mark here, a mark here, and then you'd forgot to do something else, you would get 3. An answer on the answer line can't be marked as part of working out. Okay, so if you hadn't finished the question and you put it on the answer line, you wouldn't be eligible for the working out mark that came from getting that. It's a really technical thing, but make sure you finish your working out here and then transcribe your answer across. Takes an extra second, worth it. Okay, now, this is where life gets interesting. What tends to happen is students are really, really good at calculation questions and not so good at these type of questions. Describe and explain what would happen to the size of the acceleration if the frictional forces acting on the car decrease. Right, so if the frictional forces acting on the car would decrease, then this number becomes less than 800. Okay, so let's take a look at what that would look like in our equation. So over here we would have, oh, get rid of that line, I didn't want to copy that, so get rid of that. What would I have if I had, instead of 2000 minus 800, let's just have a think about, well, if it was 2000 minus 500. That would give me 1,500 newtons as my overall force. In which case, when I get to this stage in my calculation, I'd be looking at 1,500 here, and I'd be trying to do 1,500 divided by 1,000, because my mass would still be 1,000, and I would get 1.5 for my acceleration. Okay, so in this case, if my frictional force is decreased, the effect of my acceleration would be, it would increase. Now, what's the explanation for that? And that's where people find it difficult. You get the answer okay, but we need to be able to explain our thinking. So why did that happen? With less frictional force, there would be a larger resultant force, the same mass, so more acceleration. It's probably the best way you can describe that. Just talk me through the maths. Talk me through your thinking process. What was it you did? And we'll give you that. The brakes are applied and the car begins to slow down. In which direction will the resultant force now act? Now, in order for this car to slow down, what has to happen? Remember, this force, with this force being less than this force, it's speeding up. Newton's first law says that if this force becomes equal to that force, it just stays at the same speed. So our frictional force has to now be larger than our engine force. So we'll need like 2,100 or something like that, backwards. In which case, when I do my resultant force for this, my resultant force is now in the backward direction. It goes this way because this is the larger force. It'll be 2,100, take away 2,000, and it will be overall going to the left. So which direction does it now act? This is the hard bit actually, because you have a few answers. Backwards would be completely fine because you have the car there and definitely has a back, or to the left. Answers that are not allowed. West. Now I can see where you're coming from with west, because you're like, well, up the page is north, but there's no reason to suggest that this car is traveling anything like, going to the east. Right, so look out for that. Don't use compass points unless you've been given a compass in the question. Backwards, to the left, or even just draw an arrow and you'll get the mark. Don't use compass points that aren't there. All right? Right, 47, so we've got a few minutes, we'll crack on with this one. Right, once again we've got a car. This was the same year, different exam set. So what does a resultant force always cause? Well, let's take a little look back to our thing and look. Objects accelerate when there is a resultant force. So from our knowledge bucket, we should know that what do forces always cause? They always cause acceleration. Okay, happy enough? Then the forces acting on a car traveling in a straight line are shown below. We've got 3,000 forward, 600 backwards. Combined mass of the car and its driver, that calculate the car's acceleration. Now this one doesn't look too bad. Sort of the same deal as before though. We have F resultant, which wasn't given to us, is equal to 3,000, take away 600, is equal to 2,400. We have, this time we have the mass of the car is 1200, and the acceleration is unknown. So over we come to F resultant is equal to MA. So 2,400 is equal to the mass of the object, 1,200 times A. We don't want 1,200A, so we're going to divide both sides of this equation by 1,200, and we get A is 2. Meters per second squared. The answer line says meter per second squared as well, so everybody's happy. We can just stick a 2 on there, take our 4 marks, and move on. Later in the car's journey, the forces acting on it are balanced. What's the car's acceleration at this point? So this is testing this other question, this other bit of knowledge over here, that the object will remain at rest or continue to travel in a straight line unless acted at a constant speed, unless acted on by a resultant force. Okay, so what's this thing going to do? Its acceleration, if they're balanced, well, if they weren't balanced forward, it'd be speeding up, so it would have an acceleration. If it was unbalanced backwards, it would have a deceleration, so it would have negative acceleration. This one's 1 mark. It's not accelerating. If they're balanced, by definition, it's not getting faster, and therefore it is simply 0 acceleration. Okay? And then the third question from the third set of that year, once again, we've got a car. What property does a vector quantity have that a scalar doesn't? So this is back to vectors and scalars. And like we said, from our knowledge bucket back here, these are vectors, so direction matters. So vectors, direction matters, scalars, it doesn't. So in this one, what property? The answer is direction. Newton's second law relates 3 physical quantities. State one quantity, which is a vector, and one which is a scalar. Okay, this is a little bit more interesting. So let's get back to our equation for Newton's second law, which is F resultant is equal to mass times acceleration. Right, so what we want to do, we've established what a vector has that a scalar doesn't, has direction. So we want to take a look at these and go, well, which ones make sense to, if you could say, to the left or to the right? So does it make sense to say I have an overall force to the left? Yeah, it does. So this is a vector. Does it make sense to say I have a mass of 50 kilograms to the left? No, it doesn't. Okay, so this is probably not a vector. Does it make sense to say I have an acceleration of 10 meters per second squared to the left? It does. Now, this is not a foolproof way of detecting vectors, but it's pretty good. 90% of vectors make sense if you say, well, what is it? Does it make sense to add the words to the left to it? Okay, weight is a strange one because it's a vector, but it's always towards the center of the earth. So it has a direction, but it's fixed. That's a weird one. But most of the time, saying to the left on the end of it doesn't make sense. So vector quantities, we can pick either resultant force or acceleration. Let's go acceleration, because it saves me writing the word resultant. And our scalar quantity is mass. Right, on we go. Forces acting on a car. Now this is the money shot. This is the hardest version. Okay, the forces acting on a car traveling in a straight line are shown below. We have the engine force forwards and 800 newtons backwards. The total frictional forces are 800 newtons, we got that. And the combined mass of the car and its driver are 1,400. Calculate the size of the engine force required to cause an acceleration of 3 meters per second squared. All right, cool. So what have we been given? We've been given that let's roll for the bottom. We've been given the acceleration is 3 meters per second squared, correct unit, happy. We've been given the mass of this thing is 1,400. Excellent, great. We've been given the resultant force is equal to 800. No, we haven't. No, we absolutely have not ever been given the resultant force on this car at all. We've been given the backward force. I have no idea what the forward force is, so I don't know what the resultant force is. Okay, so I have no idea what the resultant force is. I know that I'm going to have to take 800 away from something to get it, but I don't know what the something is, and this is what this question is testing. Do you understand that? Okay, so I have A, M, and F resultant, but I can actually work out what F resultant is because I can do 1,400 times 3 because I've used the equation, and I should write my equation because I'm a good student. F resultant is equal to MA, so F resultant is equal to 1,400 for the mass, 3 for the acceleration, so F resultant is equal to, and we can do this in our head, of course we can, but we're not, because we're not idiots. We're not going to sit in a pressured environment in an exam and think, oh, I know how to do that, because I might accidentally get like 3,200 or something weird. I forget to carry the 1 across. So I do my calculator and I go 4,200 newtons. So my overall force is 4,200. Now the most common mistake that anybody does is they do this calculation and they whack it into here. 4,200. And that will score them, if they do it like this, it'll score them 3 marks. If they don't put this line in here, it actually won't score, it'll only score them 2, 1 for this and 1 for this, but nothing for that because the answer is wrong. And that's why I say continue your calculation on the page. What I've worked out is the overall force is 4,200. So after all is said and done, I have a total force this way equal to 4,200 newtons. So how did I get that 4,200 newtons? Well, it must be true that my engine force, take away 800, is equal to 4,200. That has to be true, okay? Because my forward force, take away my backward force, equals my resultant force. So let's give that a symbol and bring it down into our actual working out rather than doing it up on the random set of the page. So engine force, we'll call that E minus 800 is equal to 4,200. I don't want E minus 800, I want E. So I add 800 to both sides to give me E is 5,000 newtons, and that's my answer. And I can check that answer. I can put this on the answer line, and then I can go up to my diagram and go, does that make sense? Okay, so I go up here and I put 5,000 in here and I take a look at it. Does it make sense that 5,000 forwards take away 800 backwards is going to give me 4,200 overall. Yes, that makes sense. Okay, because sometimes what students do is they accidentally take away from both sides here, and then they don't check it, and they end up getting like 3,400 here. They go, I've got 3,400 here, but I'll be taken away. No, that doesn't make sense. That's wrong. That's wrong. Okay, so that's your money shot question. That's the hardest one you can get on this. And otherwise, I think you're done with forces. Right, 5 to 9, 20 minutes to do probably the hardest topic in the entire of GCSE physics, I think. Moments. Right, now first of all, moment sucks because this word is terrible. We use this for all sorts of things that aren't what it's about in physics. Right, what moments are is its turn. Right, if something is turning, it's got a moment happening. All right, so a moment is a turn. Think about it, it's a real turning moment. Right, no, it's just a real moment. Okay, moments mean turn. I wish this was called turniness. If this was called turniness in physics, how many turniness do you have? This wouldn't be an issue. This would be really easy, but it's a language thing. Moments means turn. And here's what you need to know. And if you're on the revision train, pausing it here and actually going, right, I need to learn this, is a good idea. Right, so moments means the amount of turn. All right? There are two types of turn you can do. You can turn something either clockwise or anti-clockwise. I don't know if that's right, considering I've probably flipped the camera and then you're looking at it. Anyway, turn, clockwise, anti-clockwise. Those are your choices. Okay, calculation-wise, the size of the moment is given by two things. It depends on two things. How much force you're applying, which makes sense. Bigger force turns something more. And the second thing is the distance that force is being applied from the pivot. Okay, what is the pivot, I hear you say? Well, the pivot, if I have an object that's spinning, right? If I look at any spinning object that's turning round and round and round and round and round, every part of that object is changing position, right? If I even look at my hand here, right, and it turns round like that, right? My wrist moves upwards like this finger's moving across here, this thumb's moving up here, but this center part of my hand isn't actually going anywhere. It's just going round. At which point I could say, that's the pivot point for that turn. Okay, in truth, it's probably my wrist is the pivot point, just round about there when I'm waving. Okay, so the pivot point is the point that doesn't move when an object rotates. It just turns. It doesn't change position. Okay, now that's as far as moments goes. And you can calculate moments just using that. Moment is force times distance from pivot. 50 Newton meters clockwise. Job done. There are some special situations that if an object's sitting still, it's not rotating, then this has to be true. So this is called the principle of moments. And it's a brilliant, brilliant, brilliant idea, which is that if something's not turning, then every moment that's trying to turn it clockwise has to be balanced by all the moments trying to turn it anti-clockwise. So if you've got things like shells that have forces acting on them, there are things that are trying to turn this. And if it's not turning, if it's balanced, then everything that's trying to turn it clockwise is balancing out perfectly everything that's trying to turn it anti-clockwise. And that gives us this. This is a definition you need to learn, word perfect. For an object in rotational equilibrium, the sum of the clockwise moments is equal to the sum of the anti-clockwise moments about a fixed point. 3 marks. 1 mark for the bit in rotational equilibrium, 1 mark for the sum of the moments clockwise is equal to the sum of the moments anti-clockwise, and 3rd mark for the about a fixed point. You can say pivot there, but fixed point is better, and we'll find out in 6th year why. This shortens mathematically to MCW, the moments clockwise, is equal to the moments anti-clockwise. And you can use that shortened form in calculations, but not in definition questions. Okay, now, 3 other ideas that are somewhat near to moments is things falling over, right? If something's going to fall over because it's unstable, then it's probably because it's creating a moment. It's probably worthwhile drawing a little diagram, right? If I have a rectangle like this, and I have it sat on the ground like this, right? You would probably all agree that that looks pretty stable. It's not going to fall over. If I tip it like this, though, and we're to let it go, I think almost everybody has an intuitive sense that it's going to fall over. It's going to fall over onto the long flat side. The question is why? And the reason for that is, first of all, the center of gravity, this sort of midpoint here, if it's a completely uniform object, the middle of that object has a center of gravity. And this is the perfect balance point for that object. And the center of gravity, if I'm drawing a diagram, is the point where I can draw my weight arrow from. Okay, so I could draw the weight arrow straight down from my center of gravity. Then I could say, well, this is now a moment situation because I've got a pivot here. This thing's trying to turn and this little corner is the only bit that's not going to move. And I can see that I have a force, I have a distance from the pivot, I've got nothing to balance it. This thing is going to rotate this way, it's going to topple. Okay, so it's not stable, it's falling over. And an object is unstable if the line of action of the weight, that's this one, is outside of the base of the object. Well, the base of the object's here, the line of action of the weight is well outside that base, and therefore it's going to fall. And it's going to fall and land like this. At this point, the center of gravity will be here, the line of action of the center of gravity will be down there, and look, that's back inside its newly established base, and this is nice and stable again. So boom. That's why when you fall over, you don't keep falling over. You've re-established a nice stable position. Okay, to make things as stable as possible, you want to do two things. If you want to improve your stability of anything, to make it harder to knock over, you lower your center of gravity and you widen your base. Okay, so anybody who does like martial arts sports will notice that the person kind of spreads their legs out and then gets low. So they expand their base and they lower themselves down. If you're a rugby player and you're going into a tackle, you drop your height, you get low and you hit hard, and what you're trying to do is wrap a person's legs tight so that you make their weight fall outside their center of gravity, and therefore they can't do anything other than fall over. Okay, that's moments. Now let's take a try at some questions. So let's go. So this looks fun. We have a uniform meter ruler and it's held in position by exerting a vertical force of 0.5 newtons in the upward direction. A force X acts downwards at the midpoint of the ruler. Name this force. Well, what's happening at the midpoint? Well, the midpoint is that imaginary spot, remember, that we called the center of gravity. So let's go back to our knowledge point and go, the center of gravity, the point where all the weight of the object appears to act. So this force must be, please excuse my dog, must be the weight of the object. Okay? What is the name given to the midpoint of the ruler? Oh, happy days. I worked out the weight from knowing that the center of the midpoint of that ruler is called the center of gravity. Okay, the center of gravity is the point where all of your weight appears to act. Now, sometimes you can get people saying that it's the center of mass. The center of mass is where all your mass appears to be concentrated. They're roughly the same thing on planet Earth, though they can get a wee bit weird when you do certain other things to them. So weight and gravity are generally linked to each other, so call it the center of gravity, and the thing that comes from it is the weight of the object, especially when we're talking about a force. Okay, so use the principle of moments. That's nice of them to tell me what to do, to calculate the force X. So before I even start, I know that I'm going to use the principle of moments, which says that the moments clockwise are equal to the moments anti-clockwise. I'm going to write that down because that's actually worth a mark. Right, so let's get up here and figure out what's going on. Now this question has been actually very helpful. It's already identified for me the pivot. So what I want to do is I want to identify some distances from the pivot for these forces. I need to know how far away this force X is from the pivot, and I also need to know how far away from the pivot this 0.5 Newton one is, so I can do my two distance from pivot calculations. Okay, so let's have a look. A uniform meter rule. Ah, there it is. And they're nasty as well because they used the word meter. They didn't go 1.0 meters to give you a number. We had to go and read this. So we know that this whole thing is a meter long. It's held in horizontal position by exerting a vertical force of 0.5 newtons as shown. It looks very much like our pivot is at the very end, so we can use the fact that it's a meter ruler and that this is in the midpoint to get the rest of these details. So this distance here has to be 50 centimeters, right? Absolutely has to be 50 centimeters, no question of it. And since that's 10 centimeters, the distance from the pivot up here has to be 90 centimeters. So 90 centimeters up here. Okay, Now the next thing I need to know is which one's clockwise and which one's trying to go anti-clockwise. And this can be somewhat difficult. But what I'm going to do is, if I'm in an exam, I'm going to set my pen down along here. And I'm going to hold it at this end, and I'm going to push down in the direction of X. Ooh, pardon me. I'm going to push down with X and see what happens. If I push down my pen, my pen's going to rotate this way. And that's the way that the clock goes. So this one is clockwise. And over here, if I lay my pen out and push upwards, my pen's going to rotate this way because I've held it at my pivot. So that's going the opposite way the clock goes. So that's anti-clockwise. So again, on my diagram in my exam, I'm writing all over it. This says clockwise and this one is anti-clockwise. Okay. All right, nice one. So let's calculate my clockwise moment. Well, my clockwise moment, I'm going to use the equation moment equals force times the distance from the pivot, dFp. And I put the little FP down here to remind myself that it's from the pivot. And this is my first force. There are two forces in this diagram, so it's going to be force 1, and there are multiple distances from the pivot, so this is distance from the pivot 1. And then on the other side we have a second force, but it's going anti-clockwise, multiplied by the distance from the pivot 2. Okay, so what we're going to do is we're going to solve both sides of this equation, keeping them equal to each other. What you could also do is you could go and work out the clockwise moment, work out the anti-clockwise moment, and then bring them together at the end. But this is a little bit more quick. So moment clockwise is force 1 times distance from pivot 1. So what's clockwise? Clockwise, my force is X, and its distance from the pivot is 50. So let's get that in here instead of these annoying letters. So we want 50 multiplied by, what did we say it was? 50, sorry, try that again. The force was X, try and keep things nice and neat, multiplied by the distance from the pivot, which was 50 centimeters, is equal to the second force, which was 0.5, times its distance from the pivot, which was 90. Okay, so solving that out, we get 50x is equal to 45. I don't want 50x, I want just x, so I'm going to divide both sides by 50. So over I go to my calculator. I can do this in my head. I'm good at maths, but I'm going to make sure I'm going to put 45 divided by 50, which is 0.9. And that's a force, so it's going to be in newtons. I've completed my working out. So down in here, I put 0.9 on the answer line, and I take my 4 marks. Okay, so this is how we solve this problem. All of the thinking is done on the diagram up here, and then once we get down here, it's just execute. Just bang, 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 bang. Do your thinking up here, and then finish it. Right, so let's take a look at a different one. We've got a couple more to go. Two objects, A and B, are placed on a level surface as shown below. Mark with an X the position of the centre of gravity of each object. This is a slightly poorly worded question because I don't know that they are nice and uniform objects made of the same material, all consistently laid out throughout, but I have no reason to think otherwise. So these are regular geometric shapes, and the centre of gravity of a regular geometric shape is in the centre. Get your ruler out and make as good an effort of it as possible, but it'll inspect by eye. Like that. That looks about right. So boom, that's that one done. Tick. A third object, C, is now added. State which object A, B, or C is the most stable and give 2 reasons why. Well, back to our knowledge bucket. Okay. And we have for stability, get rid of that side bit. Okay. For stability, we want low center, move my head out of the way, low centre of gravity and wide base equals more stable. So back we go to our question, which is down here somewhere. There it is. So which object is most stable? It's going to be the one with the widest base and the lowest centre of gravity. So centre of gravity in this one here, here, and here. So C definitely is the most stable. And why? Because it meets our 2 conditions. It has a low centre of gravity and it has the widest base. Okay, notice I didn't say just wide base because B has a wide base compared to A. Okay, and I could just say lowest centre of gravity and widest base, and therefore it is most stable. Right, onward. State in words the principle of moments. Include the unit in which a moment is measured. Oh, brilliant, right. So this is literally just grab this from our knowledge bank. We have to know this. So bang, copy from your brain, come to your question, paste from your brain. There is no thinking required here at all. Except for this little bit here, unit. Now, we can either know this or we can work this out. The moment is equal to the force times the distance from the pivot. So what's the unit for a moment? Well, the unit for force is in Newton, and the unit for distance from the pivot is probably meters, but it is allowed to be other units. Newton centimeters are legitimate. Newton millimeters are also legitimate. Okay, Newton meters is the most common and is therefore the one that I would plump for in here. But you noticed in our last question, we were quite happy working with 90 centimeters and 50 centimeters. That wasn't an issue. It is in some other areas of physics that you do have to be really careful, like acceleration. You have to be in newtons, you have to be in meters per second squared, you have to be in kilograms. Here, moments, a little more relaxed in moments. Just provided our forces in newtons, we can pretty much do whatever we like. Okay, so we're into another one here. We have 160 Newton weight is hung from a uniform rectangular beam so that it is balanced as shown below. So we've got it balanced, we've got our pivot point marked here, that's lovely. The centre of gravity of the beam is labelled X and the beam has a weight of 200 newtons. Okay, cool. So our first piece of information is that we have the centre of gravity. The centre of gravity is the point at which the weight appears to act, and we've been told that it's got 200 newtons. So we can put 200 newton downward arrow at X. Okay, before we even do anything else, I'd be away and putting that in just to make sure. All right, we're told it's balanced. We've got 160 newton weight. Calculate the distance from the pivot to the 160 newton weight. Oh, okay, well, that seems reasonable. We should be able to do that. What we need to do is we need to go, right, well, here's the pivot. We need to find out how far away that is. That's what we've been asked to do. And we also need to know how far away this is. We've been given the two forces. Okay, we've been asked to find one of the distances. So this distance must be findable. Now this says a uniform rectangular beam. So we like the word uniform. That means it's nice and stable throughout. If it's 1.2 along, then that means this halfway point here must be 0.6 meters in. Because it's at the midpoint, because it's uniform. If that distance is 0.6 to the middle, this is 0.4 of it, then this distance here is 0.2. All right. Now, we don't know what this distance is, so let's call this distance just D for distance. Though we do have some suspicions about it, like where we know that it's going to be less than 0.4, otherwise it doesn't make sense in our diagram. So that gives us an idea as to the kind of range of answers we want. Okay, so it's balanced. So the principle of moments applies. So we're going to start with our statement, moments clockwise is equal to moments anti-clockwise. Next thing to do, identify which ones are clockwise and anti-clockwise. So imagine setting our pen down and pushing this way, and that's going the wrong way to the clock. So this one is anti-clockwise, and this one is going the same direction as the clock, so this one's clockwise. Okay, so on my clockwise side, let's do my calculations. So for moments clockwise, I want force 1 times the distance from the pivot 1, so dFp1. I'll roll this up the screen a bit. Has to equal force 2, and there only are two forces in this, times distance from pivot 2. Now you'll only ever be asked to deal with things that have two forces on it, but when we get you to 6th year, we'll deal with multiple forces, so it's a good idea to label them force 1 and force 2, so that when you get force 3, 4, 5 and 6, you can still cope. Okay, so on the clockwise side, we have a force of 200, a distance from the pivot of 0.2. On our anti-clockwise side, we have a force of 160 and a distance from the pivot of D, which is what we're trying to find out. Okay, so let's simplify that side. Calculator, again, we go 200 times 0.2, and that gives me 40 is equal to 160 D. I don't want 160D, so I divide both sides by 160, and I get 0.25 is equal to D. And I'm happy with that because that answer is less than 0.4, and it's in the, looking at the diagram, 0.25 meters looks legit. So onto my answer line, I get a 0.25, pick up my 3 marks, over and out. Last question for the night, you're doing brilliantly. State in words the principle of moments and include a unit in which it's measured. It's a carbon copy of this. It's such a common question that knowing that from your brain bank, worth marks all day and all night. If moments comes up, knowing this is important. Okay, unit, once again, newton meters, but you know what? Just to be cocky, I'm going to stick newton meters or newton centimeters in here because it says include a unit, not the unit. Notice that. The word a is here because there isn't a specific unit to measure moments in. You're allowed to chop and change. And look at this. Once again, we have a uniform beam, weight 150, center of gravity X. So at this point, we can go straight up to bang, in it goes here. We've got 150 newtons on the downward, 150 newtons, lovely jubbly, and it goes 160 centimeters straight on. So I know that the midpoint here is 80. I can almost predict the question now, and this is the beauty of doing past paper questions, that I don't want you to be thinking hard in the exam. I want you to be bored. You should be like, oh, this question, I've done this. Let's do it again. No bother at all, just go through the motions. Right, so if that's 80, that's 60, then this distance here, logically, must be 20 centimeters. The pivot. What are we being asked? By first finding the distance y, okay, that looks like fun, calculate how far the 200 Newton weight was moved to balance the beam. Oh, interesting. Right, okay, we need to read this properly. When a 200 Newton weight is hung on the beam 25 centimeters from the pivot, boom, 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 it does not balance. The 200 Newton weight is moved until the beam is balanced as shown below. Oh, that's nasty. That is nasty. So let's calculate the distance y that it has to get. So this is really important because I could have misread that question heavily there. So I like this. I like this. This is going to be worth 5 marks, isn't it? It is. It's worth 5 marks. All right, so let's go. We start with moments clockwise is equal to moments anti-clockwise. Bang, straight up. 1 mark on the board we're playing. Right. So let's identify which ones are clockwise and which ones are anti-clockwise. So we lay our little pen down and we go, right, that's going to try and spin it that way. So that's anti-clockwise. So let's get my pen and mark that in, ACW. And this one here, logically going to be clockwise. So my next line comes straight out. We have one force, so force 1, and its distance from the pivot 1, dFp, has to equal force 2 times its distance from the pivot. And that's distance from the pivot 2. And a 1 over here. All right, lovely, lovely. So for our clockwise force, what was our force again? Let's try and look that up. Clockwise, we had 200. Its distance from the pivot is y, is equal to my anti-clockwise force, which is 150, times its distance from the pivot, which we worked out was 20 centimeters. All right, so 200y has to equal 150 times 20. So we go and grab our calculator again. 150 times 20 equals 3,000. So y equals, we take 3,000 and we divide that by 200, and that's going to give me 15 centimeters. Right, okay. So this distance is only 15 centimeters from the pivot. So that's 15 centimeters. Now what were we told? When the weight is hung on the beam 25 centimeters from the pivot, it doesn't balance. Right, so we went 25 centimeters out by accident and it fell over, and I should have been at 15. So I went there and I needed to come back to here. How far did I need to come back? Well, I went out to 25. I had to come back to the 15 centimeter mark. So I needed to come back 10 centimeters. And in which way did I need to move? Now, we'll be generally pretty generous here with things like left or an arrow or whatever. An arrow is probably the best thing to do here, just that way and you're done. But towards the pivot is probably the best way to phrase that. All right, folks, that was massively quick and dirty in terms of that, but ended up being quite a long video. What's that, 48 minutes. But if you stuck to the end, thank you so much for hanging about. Hopefully this has cleared up a little bit of forces and moments for you. Next week we'll hit energy, and then the week after that it's nuclear, and you should be ready to go for your exam. So with all that said, thank you for your attention, and don't forget, physics rocks. It's true.